Okay, so thanks everyone for joining. This talk is about verification of concurrent programs and more specifically about verification by means of stateless model checking. So stateless model checking is a form of bounded verification where if we want to verify a concurrent program, we enumerate all of its interleavings one by one, and then we check that some safety property that we care about holds at each interleaving. Now, of course, this does not scale. So there have been two major approaches proposed to tackle this state space explosion problem. One of them is partial reduction, and the other one is symmetry reduction. So symmetry reduction says you can avoid ordering threads that are symmetric, that are running the same code. And partial reduction says that you can avoid ordering independent actions. So let's see what these techniques will do with a couple of examples. So in this program here, we have x initially being 0, and then we have n threads, each one doing an atomic increment on x. If we try to verify this with stateless model checking, then we'll enumerate n factorial executions, right? N threads and instructions, so n factorial permutations. And in this case, if we apply partial reduction on top of stateless model checking, we actually get no reduction. And the reason is that all of these instructions are conflicting. They are all writing x, so partial reduction considers them conflicting, and we'll explore still n factorial interleavings. If we do symmetry reduction, on the other hand, we'll just explore one interleaving, and the idea is that the threads are running exactly the same code. The result is going to be the same no matter what. We just explore one and we're done. In this example, we have n variables, different variables, initially 0, and each thread is writing a different variable. Again, stateless model checking, n factorial. In this case, though, partial reduction can verify this program by exploring a single execution. And the idea is that each thread writes a different variable, right? So no matter which interleaving I pick among these n factorial, the end result is going to be the same. Each of these variables has the same value. And for symmetry reduction, again, here we get no reduction because these threads are not symmetric. So these techniques are somewhat similar. One way to view both of them is by the equivalence partitioning that they induce on the interleaving. So they effectively partition the interleavings into equivalence classes and then try to explore one interleaving per equivalence class. But so far, these techniques were incompatible. So we couldn't get the strength from both techniques into one. Now, you might be thinking, well, why do you care? If a program is symmetric, if all the threads are running the same code, can you just do symmetry reduction? And another point that I want to make is that actually either technique is inadequate, and I have a different example there, which is essentially somewhat the combination of the previous two. So each thread does a fetch and add in the beginning, and then from the index it reads, it writes this value to from the value it reads for x, it writes it to an index in the array A. Now, what's interesting about this program in some sense is that each thread is going to read a different value for I because these are atomic increments. So in fact, when these threads manipulate the array A, each thread is going to manipulate a different index, right? So if we look at the numbers there, ignoring the stateless model checking, partial reduction can verify this with n factorial interleavings. Why? Because there are n fetch and adds, so n factorial ways to order the fetch and adds, which are conflicting for partial reduction. But then partial reduction is smart enough to understand that these writes to A are all in different locations, so it doesn't have to order them. But in this case, if we try to do symmetry reduction sees that these are threads that are running the same code. And in fact, it will just order the fetch and add instructions in one way, say left to right. But at that point, symmetry breaks because each thread read a different value, so the local state is different. So from that point onwards, in this context of stateless model checking, symmetry reduction is of no use, and it will enumerate not only the orderings among the accesses to A, but also the orderings among the accesses to A and the fetch and adds. So in fact, the number that we get there is a double factorial of odd numbers, which is even larger than what partial reduction alone will enumerate. Right, so my point here is that symmetry reduction does not subsume partial reduction, even if the program under test is symmetric. And this is where this talk comes into play. I'll talk to you about SPORE, which is a combination of POR and SR. And for this example, it can verify it by exploring a single interleaving. So SPORE is the first combination of symmetry and partial reduction. It is sound, complete, and optimal, meaning no false positives. It explores the full state space of the program, and it does no redundant work. It is parametric in the choice of the memory model. I'll be talking about sequential consistency and interleavings, but these results carry over to weak memory as well. It leverages internal symmetries, which is a novel notion that we introduced in this paper, and I'll discuss in a bit. And of course, it's faster than the state of the art if the programs have some sort of a symmetry. So let me tell you how SPORE combines symmetry reduction and partial reduction. So the way we do this is by adding symmetry reduction on top of partial reduction, and in fact on top of a partial reduction algorithm called trust. What's the key idea in trust? The key idea is that these equivalence classes that the interleavings of a program create can be represented as execution graphs. So if we want to verify a program, explore one interleaving from each equivalence class, so to speak, we can just enumerate these graphs. And I have an example here. So X is initially 0, 3 threads manipulate X. This program has 6 interleavings. 4 equivalence classes represented by 4 graphs, which are these 4. So in these graphs, the nodes correspond to instructions. This init node here corresponds to the initializing write to X. So yeah, this is write X, read X, and so on. The black edges denote program order. They connect the initializing write to the first event of each thread. And what's more interesting are the green edges, which show where the reads are reading from. Right? So for example, there, these reads are reading 0, 0, 0. Here is 0 and 1, and so on. Right? So trust would verify this program by enumerating these 4 graphs. Now SPORE also leverages this idea of graphs. And in fact, what we observe is that actually these graphs are a very nice way to identify symmetries. Right? So for example, here, thread 2 and thread 3 are running the same code, right? They are symmetric. And we can see that on the execution graphs. So these 2 graphs can be obtained one from the other just by swapping threads 2 and thread 3. And so what SPORE says is that for these graphs that are symmetric, you can identify one of them as a representative one, and then only generate representative graphs. Right? Now, so for the full graphs that correspond to a given program, for the ones that are symmetric, we pick representatives, we enumerate these ones. Now, this is easier said than done. So it's quite complicated to actually get all the completeness and optimality guarantees, but I don't have the time to go into details. If you're interested in that, please read our paper. Now, the second thing I'd like to talk a bit about is internal symmetries, because this is introduced in this paper. And I'll explain what this is with an example. The example is a Michalis queue. This is a lock-free queue implementation. I have the code for enqueuing an item there. I'll go over it in a second. Essentially, this queue is represented by a pair of head and tail. Items are enqueued at the back, at the tail, and dequeued from the front. So now suppose we have one thread that wants to enqueue an item. So it will start executing enqueue. It will allocate some memory, set some value to the new node, and set the next pointer. So essentially, this is what these first 3 lines are doing. And then it will enter this do-while loop, which is the main enqueuing loop. In the beginning, it reads tail. It reads the next pointer of tail, and then it reads tail again. This is because it wants to read tail and next in one atomic step without tail changing in the meantime. So it effectively will read these 2 pointers there, these 2. it will check if next is null. If next is null, it can proceed with enqueuing the item. In this case, it's null. So it will try to do this compare and swap. So if next hasn't changed in the meantime, it will try to enqueue the new node. So this is, let's assume it succeeds. And then finally, what happens there is that T1 notices that tail is now lagging, right? It's not pointing to the actual tail anymore. So it will try to advance the tail. But now suppose that before it does this, a new thread comes along and tries to do the same thing. So it allocates some memory for a new node. It will check tail and next. It will read the same values for tail and next, right? Nothing has changed. But then when it checks if next is null, next is not null at this point. And so what T2 is going to try and do now is it's going to try and help T1. It sees that some other thread hasn't finished with its enqueue, so it's going to try and help it. And now this is a bit problematic in terms of verification because we have contention. And so this contention on tail hinders verification. Right? And you can take my word for it, then if we have k threads, this will create a k factorial overhead. Now the key observation that SPORE does, and that's behind internal symmetries, is that these conflicting operations on tail are identical, meaning that they are actually trying to do the exact same operation, but they're also idempotent in the sense that we have no way of knowing which of the two operations succeeds, right? There's no control flow in the cast. We cannot know which thread succeeded. And so this is what SPORE leverages. And it says that it leverages by splitting these operations into a main one and some helping ones, which is done by annotating the input program. And then it tries to only explore executions where the main one succeeds. So all the helping operations are effectively treated as no wops. Right? And this gives an exponential reduction. Is this sound? In general, no, and I have an example on when it is not sound to do this. So in this program, x and y are initially 0, and we've erroneously annotated. So these two cases write the same value and so on. We've erroneously annotated this one as main and this one as helping. Now, if T3 only reads from the main one, then it will miss the bug. The idea is that if this read of x reads from there, then when T3 reads from y, it will see this write to y there because of the synchronization induced by the cast. But if we were to explore the execution where the read of x reads from there, then the read of y can read 0 and we would find the assertion violation. Right? So in general, this is not sound. But SPORE presents sufficient conditions for leveraging these operations and for identifying when this is sound. And something that I haven't said, so main and helping do not just have to be cases, they can be functions, as long as they satisfy these conditions that SPORE imposes. So essentially, you don't want to be able to distinguish which one is the one that succeeded based on synchronization, based on control flow, and so on. So this is a form where we can distinguish which one succeeded based on the induced synchronization. However, as long as these conditions apply and then internal symmetries can be leveraged, then they can also be leveraged in non-symmetric programs. So the threads that are annotated, the operations that are annotated as main and helping do not need to live in symmetric threads. They can be in threads that are not symmetric. Okay, and just a bit of evaluation. So essentially what we wanted to show is that SPORE scales well enough to verify realistic implementations, and we got some real-world data structures, also some data structure from some widely used concurrent libraries, and we wanted to see how well SPORE scales. We tried various configurations. So x-axis is number of threads, y-axis is number of executions, logarithmic. And the takeaway is that, of course, SPORE scales better than plain DPOR, say, or plain SR. Stateless model checking, I think, doesn't appear. It just times out for most of these cases. And of course, having both internal symmetries and symmetry reduction is better than just having one of them. We have various configurations. And that's all I had. So SPORE is the first combination of symmetry and partial reduction. It's sound complete and optimal, and it leverages this novel notion of internal symmetries that we have in the paper. This is the end of my talk. I'm happy to take your questions.
We have time for a few questions. So I have one question. So where do you go from here? So what's the sort of directions that this sort of leads you to? New directions?
So one direction that I think is interesting is to try and relax the conditions that we have on internal symmetry. So in principle, it's not very clear how generic these main and helping functions that we have are. Now we have some restrictions. Essentially what we say now is that these idempotent operations are a series of reads that are followed by a cas. But perhaps we could allow more expressiveness in these functions. We could allow some form of writes or in general, relax these conditions and see if we can, that way, capture more patterns that appear in concurrent programs that we're not able to capture now. Mm-hmm. And then, of course, there are we could also try and see if there are similar symmetries in different classes of programs, say persistency programs or some other class that we could leverage.
Just as a follow-on, can you just sort of briefly give some intuition on what the interesting challenges are with the memory model issues? How does that sort of change the kind of reasoning that you have to do in order to be able to keep soundness and optimality?
It's a bit tricky.
Okay.
So some of the completeness issues are not even related to the memory model. One way to summarize the problem is that DPOR needs to pass through certain configurations to generate some others. It's some sort of a DFS exploration. When you try to add symmetry reduction on top of that, some of the configurations that DPOR wants to go through, you might want to drop because they are non-symmetric, they are non-representative executions according to the notion of representative that you have. So what you want to do is have a notion of representative executions that DPOR will respect and that will pass through so that you're able to generate all of them.
Understood. Thank you.
Thanks.
If there are no other questions, let's thank Michalis. Oh, sorry. Oh, please come to the mic.
Excuse me. So, I mean, there are some works that, they use commutations of,
right.
They try to prove that some operations commute and so on.
Right.
And this can be applied, to programs with complex data structures and so on. I mean, as far as you have, if you have, let's say, decision procedure for deciding this commutativity, this can be. So how this is, can be compared with what you are trying to do, or whether they are complementary, or how they...
I think it's complementary in the sense that I suspect that commutativity conditions, you can have them, you can have them dynamically, even if the threads are not symmetric and so on, you can have some commutativity conditions. But then how it compares in terms of reduction, I don't have an answer, but it's definitely interesting to see if you can,
Because I think these examples, I'm not sure, but maybe their techniques for proving commutativity can show that this program can be turned to a sequential program or something like that, or maybe not.
I don't think you can do this for the. Okay, I'm not sure actually. I don't know if you can do this for any of the programs that we've considered, but in my head it's different. It's very interesting to see if you can somehow combine commutativity conditions with these kind of partial reduction algorithms. It's an interesting thing.
If there are no other questions, let's thank Michalis again.